looked at the power rule, which was this. Oh, and the other thing I need to write is, so a notation thing. Okay, the symbol d over dx is what we call an operator. And so think of it like a function, but normally functions you guys think of as taking in numbers and then they spit out some other number, right? But they don't have to take in numbers and spit out other numbers. They could take in functions and spit out other functions. And since that's a kind of a different, in some sense, different thing, we give it a different name. We call it an operator. So d over dx means take the derivative of the thing that's written to the right of it. Okay, so d over dx of f means take the derivative of f. Okay, it's just an alternate notation, because what's another way to say take the derivative of f? Yeah. Right, we could use the prime notation. So there are two sort of different sets of notation that we use here. The prime notation basically is due to Newton, and in physics, now the way Newton would actually do it is he put a dot above the variable, and they still use that in physics quite a bit. Dot notation. And in the physics context, it always means derivative where time is the variable, and that makes sense for the stuff they're doing. But the reason we keep this other notation, this d over dx sort of fraction-looking thing, that's due to Leibniz, is because it makes certain things easier. So if I want to write the power rule, which is what we sort of finished discovering last time, I can write it like that. X to the n is some function, okay? So in this case, it's just x with some power. And d over dx means, well, what's the derivative of x to some power? What was the rule we figured out? Remember? Derivative of x to a power. What was the trick we figured out last time? Yep. Yeah, so it's that. Okay, n times x to the n minus 1. And that works provided that n is a number, but it doesn't have to be an integer. It doesn't have to be a whole number. Okay, and so what we therefore have is over here on the left, and I'll just rewrite these for reference. We could think of d dx of a constant being 0 as a special case of the power rule, because a constant is really x to the 0, right? And because what's x to the 0? What's anything to the 0? 1. And so if you did the power rule to that, you'd get 0 times x to the something, and well, 0 times anything is 0, so that's that. So yeah, the derivative of a constant is 0. Now what's another way that we could see why that's true? What's the graph of a function that's a constant function look like? It's a horizontal straight line. Well, what's the slope of that thing? 0. Which is what the derivative is, right? So yeah. Trig functions, take these on faith. Oops, forgot the minus. Make sure we've got Twitch up. Derivative of sine is cosine, and the derivative of cosine is minus sine. You got to be careful with the minus. why this is true, it is actually, you can prove it with the limit definition. And then, do you guys remember in trig in high school, there were all kinds of arcane trig identities, right? So if you use sort of the right trig identity, then you can prove those. E to the x is kind of a special function because it is its own derivative. Okay, there are only two functions that have that property, e to the x, and what's the other one? Not quite. 0, which is a really rather uninteresting function in comparison to e to the x. Okay, yeah. So, and then natural log. What's the derivative of him? Oops. Just 1 over x. This, by the way, the fact that that works is why we typically use base E stuff in calculus, because it makes that stuff happen nicely. If you use like 2 to the x or log base 7 or something, it sort of does this, but there's these annoying constants that you have to multiply by, and that's just ugly, so those are that. The one other thing to mention is that for the trig functions, this is true assuming that x is measured in radians, not in degrees. If you do it in degrees, it's kind of a mess. So we do everything in degrees. I mean, radians, sorry. Yeah, okay, Gucci? So just take these guys on faith. We didn't fully prove number 2 last time, but I think you guys kind of got the idea as to why it worked from the limit definition. And yeah, okay. So let's carry on. Okay, so we did x cubed last time, right? And it took a little bit of work. So let's do, say, x to the 4th. How about that, just for funsies? Okay, so, and so the derivative is limit h goes to 0 of f of x plus h minus f of x all over h. And that's going to be limit h goes to 0, x plus h to the 4th minus x to the 4th all over h. Okay, now, foiling this thing out to the 4th, it'd be kind of a mess. And we were running a little bit short on time last time, so this I just sort of plowed through. Okay, how do I know? Here's what it's going to come out to be. Okay, so if I FOIL all that crap out, that's what I'm going to get. Now, how do I know that it's going to be that? First off, there's a bit of a pattern here, okay? So how many terms should I get if I've got something to the 4th? A lot, but how many a lot? Well, okay, let me rephrase. After you collect like terms and simplify, how many should you end up with? Should end up with 5, okay? And notice the pattern of the powers. So the very first one is x to the 4th, then x cubed, then x squared, then x, then no x's. The h powers go the opposite way. No h's, 1, 2, 3, and 4. Okay? And then the coefficients here, I happen to know the pattern, and it comes from Pascal's triangle. Okay, so you guys ever seen that before? All right, well, this is called Pascal's triangle. So I start at the top with ones, okay? And then the way that I get the next row is each number is the sum of the two numbers sort of above it, Okay, so for example, the 2 here is the sum of 1 and 1. The 6 that's down here, or say, let me do the 4, is the sum of 1 and 3. Okay, and then that pattern continues. And those numbers, 1, 4, 6, 4, 1, are the coefficients. Okay, so notice when I FOILed all this out, what are the numbers in front? 1, 4, 6, 4, 1. Yeah? Behold the powers of math. Right, so anyway, there is a general way to write this out in terms of, did any of you guys take statistics or probability or something like that in high school? Yeah. So the parentheses thing where it's like 4 choose 2, do you guys remember what that meant? Yeah, like 4 choose 2 or 6 choose 3 for like combinations and permutations and stuff. Okay, well, so it's a thing that answers the question, like, let's say that you've got 5 t-shirts and you need to pack, you're going home for the weekend, so you need to pack 2 of them in your bag. How many different ways are there for you to pick those t-shirts? Well, 5 choose 2 is what it turns out to be, and you can figure out what the number is, right? But it turns out that these coefficients are 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. And those we call the binomial coefficients. So they turn out to be related to this just as much as they are to probability. Okay, anyway, so the important point to notice about distributing all this crap out is, what's the very first term going to be in every time we've done this? X to the whatever the power is. Well, that's exactly what we're subtracting down at the other end, right? And all the other terms that I get when I FOIL crap out have h's in them. Okay, so the one term that doesn't have an h in it gets canceled, and everybody left has an h in it, which means the next step, what can I do? Yeah, I can factor out an h, and then the step after that, I'll cancel it. Oops. So I'd have h times 4x cubed plus 6x squared h plus 4xh squared all over h. So I cancel the h, and then after I've canceled the h, there's only one term that doesn't have an h attached to it anymore. The second term from the FOILing step. Yeah? Okay. Go ahead. Oh, yeah, sorry, thank you. Not after 6x squared.
Like, shouldn't that be 6x squared h? Because you already factored out the h.
Plus 4x squared h plus h, so h cubed.
Okay, so sorry. So I need h cubed, and then that makes. Yeah. I see what you're saying. Okay, this should have an h, and then this should be 4xh squared plus h cubed. Okay, thanks. Good. All right, so now that we got everybody straight, what do we notice? Everybody has an h attached except for the very first one. And if h is going to 0, what happens to everybody but the very first one? They're all gonzo, okay? And so what's left is just the 4x cubed, which matches our pattern, right? So x to the 4th, what would the derivative be? 4x to the 4 minus 1, or 4x cubed. And so, like, this isn't proof to say, oh, well, you guys kind of see what the pattern is, but it's, a step towards that. You guys see what the pattern is. okay? The other thing and this part would take a bit more work, is this pattern works because the numbers that I'm picking for my exponents are whole numbers, right? If I start doing like x to the 7.29, I can't FOIL that out. That doesn't make sense, right? So then I have a bit of a problem. And the proof for that case is much trickier. Okay, so, all right, so let's do the one that's on the screen here. So we got f of x is x cubed. And so the derivative is 3x squared. Okay, great. All right, so a very common question, find the equation of a line tangent to the graph at a given point. What information do we need to know in order to find the equation of a line, of any line? There's two ways to answer this question. Yeah, you need to know the slope and the y-intercept, or alternatively, you can know the slope and just some point, right? The y-intercept is a specific point where x equals 0, but there's no reason we have to pick that point, right? Now, in high school and in algebra, it was often very convenient to use the y-intercept. I mean, it makes it pretty easy to graph these things, right? But we don't have to choose that point. We could choose any other point. Okay, so what we need to remind ourselves of is so-called point-slope form of a line, okay? And so you guys know the mx plus b form, right? That's the slope-intercept version that you used all the time in high school. The other version is this, okay? And what are the things here? What is everybody? So what's m? Yeah, because the word slope totally has the letter m in it. Actually, have I mentioned the best guess as to why m is what we use for slope? Because it's certainly not the word, right? The letter m is not in that word, right? The best guess that I've seen is it's from French monter, which means to climb. So, yeah. But that's the best guess that anybody's got. All right, and then the point, what are the coordinates? It's at x naught, y naught. And this is just sort of a Britishism that sticks in math language. Subscripts of 0 we read as naught in a UGHT, not 0. So x sub 0, that works too, but for some reason we just say x naught. Okay. All right, so the coordinates of the point and the slope. If we have those two things, we can write the equation of a line. And you can always turn this into mx plus b form, because if I just multiply that out, then this quantity here is b. Okay, so you can always turn it from this form into mx plus b form if you really want, for like graphing it or something. But it's perfectly fine the way it is. And the reason that this form is really handy is because if I want to find the equation of a tangent line, I know the point at which I need to be tangent, and the derivative will tell me the slope. So this version of the equation makes it real easy. Okay? Okay, so what's the x-coordinate that we're interested in here? So tangent at x equals, what point did we pick, -1? Do we know the y-coordinate of the point? Okay, we know the x-coordinate's -1. How did you get the y-coordinate was -1? Yeah, you plugged it in where? to the function f, okay? So if you need to know the y-coordinate of something, you just plug it into the original function, and in this particular problem, it happens to be the same as -1, okay? Slope is what? Well, what do I have to plug in where to get the slope? Yeah. To f prime, okay? So I got to plug the thing into the right function. In this case, I'm going to plug it into f prime. So f prime of -1 is 3 times -1 squared, which is 3. Okay? So we know our point, we know our slope. Now what? Y minus the y-coordinate is slope times x minus the x-coordinate. Okay, why did I have pluses there and when I said minus? Yes. It depends on what the definition of is. Sorry. My terrible handwriting. Yeah, exactly. I'm subtracting negatives, so the signs flip. Okay, yeah. And, you know, when you're in a hurry, that's the kind of place you'll make a mistake. So, yeah. Okay, so there's our equation. And if I wanted to graph this, okay, so this is the other reason that the slope-intercept form is the one that you guys typically used a lot in high school, because can I punch that thing into a calculator as written? No. It needs to be in y equals blah form, right? So right now it's an equation, not a function, but I could fix it. And do it like this, and then punch that into something to graph it, okay? So, yeah, that was the other reason that I think that you guys typically used, or that in high school we typically, like to graph it we need a function, usually, okay? Now Mathematica actually can graph equations rather than functions, because it's slick like that, but you have to do it in a different way that's not as obvious, so yeah. Okay, so what we want to do next is, for this part, I'm actually just going to use Mathematica, so let me switch over on the Elgato here. Okay, and so let's see. I need to bind a button to. I don't have a button on my stream link for Mathematica yet. I need to do that. Okay, so let's put, first off, my original function in this case was x cubed. So I'm going to plot x cubed. And the point that we were interested in was at -1. So let me do the range of my plot from -2 to 2, just so that we see everything we're interested in. Okay, what was the equation of the tangent of the tangent line? As a function, it was 3x plus 2, right? So I'll go ahead and graph that also. And if I do it right, okay, what do we see? The blue line is our original, x cubed. Okay, that's fine. The orange line is our tangent. And does it look like it's tangent at the actual point? That would be right here. Does that look pretty good? Yeah, okay. And now the other thing is, does the slope look like it's 3 from the graph? Yes and no. Right? It doesn't look like it's 3 until you realize that the y scale and the x scale are very different. Okay? So just keep that in mind, right, when you're graphing it, that the ratio of the x and y may not be what you think it is. Okay, so there's that. And then while we're at it, what was the formula for the derivative that we got? 3x squared, okay? So let me throw that on there in green. And in fact, actually, let me pull out the tangent line just for, just so that the graph isn't too cluttered at the moment, okay? But what can we notice about that? So when is the slope of the tangent line 0? At x equals 0, which is exactly where the orange curve touches the x-axis, okay? To the right of 0, what is true about the derivatives of the orange curve? It slopes, well, okay. Which function are we talking about, the derivative or the original? The derivative is positive. What does that mean about the slopes of the original? They are also positive, okay? So notice that whenever the dude on the right, or sorry, the blue guy, right, slopes are positive exactly where the orange curve is positive. Similarly, where are the slopes negative on the blue curve?
Where the derivative is negative.
Which does that ever happen on this particular graph? Okay, so the correct answer would be nowhere in this case. And that's only because x cubed has always got positive slopes. Okay, fine. Right, now, what would the derivative of 3x squared be? We got a bit of an issue there. What's the derivative of x squared? So what do you think the derivative of 3x squared is? How about 6x? Yes, and that's exactly correct. So let me throw this out there. And notice, what are the slopes of the orange curve? Negative slopes to the left of 0, positive slopes to the right, and notice what the green curve is. Exactly that. The green curve is negative to the left of 0 and positive to the right. Oh, that's kind of cool. Okay, so does that kind of make sense? All right, now let's go back, because there was one other thing that we could do here. So actually, let me just use Mathematica for this part. Let me define a function, and I'm going to call that the original x cubed. And I want negative 1.1. Okay? If I plug negative 1.1 into the function and cube it, I would get that, negative 1.331. Okay, great, whatever. Okay, how could I have approximated that without actually having plugged it into the function? Use the tangent line. Okay, so let me go back and let me regraph the function and the tangent line. Okay, and here I'm going to plot it on negative 2 to 0 so that I've got negative 1, the point of interest, sort of right in the middle. Okay, when I'm really close to the point of tangency, is there a huge difference between the orange line and the blue curve? Like are they really close to each other? Yeah. The further I get away from negative 1, the further and further they drift apart. Okay, so if I want to know what is f of negative 1.1, I'm basically asking what is the y value right there where my mouse cursor is, along the blue line. Well, isn't that pretty dang close to where it would be on the orange line? Yeah, okay. So what I can do is I can say, all right, what was my tangent function? I'll call it g. It was 3x plus 2. That was my the thing I got after I did the tangent line and made it into a function, okay? If I plug negative 1.1 into that, what do I get? Well, that's pretty close. to the correct answer, which was negative 1.331. Okay, so does that make sense? So I can use the tangent line to approximate the function for values that are relatively close to the point of tangency. The further away you get, the worse the error will be. But the closer you are, the better it'll be. Okay. All right. So does that kind of make sense? And think about this from a. I mean, when I'm demonstrating this with Mathematica, it kind of it sort of defeats the purpose, because it was just as easy, if not easier, to type in 1.1 cubed than it was to do all this other rigmarole. Okay, but imagine a world where you didn't have computers, calculators, or anything like that. Okay, so let's go back 100 years ago. 100 years ago, how many computers were there in the world? 0. Okay, or it depended on what you called a computer. So 100 years ago, computer was a job title, not the name of an object. Often, actually, interestingly enough, and this was especially true when World War II broke out in this country and in England, who were all the computers? They were all women, right? Because the men were off in war. Yeah. And actually, has anybody seen the movie Hidden Figures, or read the book, or read the book? Yeah, that tells the story of a couple of them from NASA. What the movie kind of cuts out is that they had been working for the predecessors to NASA since World War II, whereas that movie starts in the 60s, right? So anyway, I love that opening scene with the police car. And they're like, woohoo! So anyway, right. So if you were in a situation where doing the actual function evaluation was expensive or just not practical, you could get pretty dang close by using the derivative, the tangent line approximation. And the tangent line approximation, notice that it only requires us to multiply something by 3 and add 2. Well, adding 2 is real easy. Multiplying by 3, that's pretty easy to do by hand also. Whereas doing 1.1 cubed, I mean, even if you had a slide rule, it's not going to be all that great. You guys know what slide rules are? Yeah. Have you ever used one? I've got a box full of them in my office. They're really cool. And preview of coming attractions. If you guys take MAT111, and then in the fall, then in the spring you could take MAT277 with me on spherical trigonometry, and I'll teach you how to use a slide rule. So anyway, along with other very arcane skills. So for example, since you guys have to get up pretty early to come to class, it was a nice morning. I mean, it's cold, but it's relatively clear out, and the sunrise is quite beautiful, right? Where is the sun along the horizon at sunrise? Over there, right? Okay, but where is over there? Southeast. Yeah, it's southeast-ish, but is it always at the exact same spot? No. And when does it rise due east? Only 2 days of the year. Yeah, on the 2 equinoxes. Okay, and on the winter solstice, which was in late December, it's as far south as it gets, and on the summer solstice, it's as far north as it gets. I can tell you how to calculate, if you know the latitude of where you are on Earth and the time of year, where it's going to be along the horizon. Huh? Yeah, it is pretty groovy, right? But, you know, if you were on a ship back in the day, then in the middle of the ocean, that'd be pretty handy knowledge, right? So, okay. So let's go back to the sheet. And I don't think I need to have a button for preview also. Okay, so we sketched everything, and yeah. Okay, so, oops, there's a typo there. So, a couple of rules, like, so far the functions we've dealt with for computing the derivatives were all relatively, like they were simple individual things. If I have two functions added together, what's the derivative of the sum of those two functions? Well, how did this work with limits? What was the limit of a sum? Sum of the limits. And since the derivative is defined in terms of a limit, everything that's true about limits will pretty much work for derivatives also, okay? With some exceptions, but we'll talk about those. Okay, so in particular, if you have the sum or difference of two functions, the derivative is the sum or difference of the individual derivatives. And if you have a constant out front, it just sort of comes along for the ride. Okay, so let's take this horrible, nasty polynomial. Okay, what's the derivative of x to the fourth? Just 4x cubed. So what's the derivative of 14x to the fourth? Careful. Yeah, so how are you computing that? You're doing 14 times 4, x cubed. Right, so the coefficient, the 14 stays put. The 4 comes out front and multiplies it, and then we just have to figure out whatever 4 times 14 is. And then what's the new exponent? X cubed, okay? Similarly, let's do the next one, because there the arithmetic's easier. 7x cubed becomes, well, what's the derivative of x cubed? Huh? 3x squared, okay. But there's the 7 hanging around, so what's the derivative of 7x cubed? 21x squared, okay. And then, so can we do this for each term individually? And so then how do we put it all together? Just add it all up, okay? So what's the derivative of this? It'd be, what did we say 4 times 14 was? 56. 56x cubed plus 21x squared plus 6x minus plus 0. Okay, which I wouldn't actually write the plus 0, but for sake of pedantry, I'll say it just so that we're all on the same page. Okay, does that make sense? Yeah? Sums and differences, super easy, no problems. Okay. Now, similarly, so this is our check for understanding. See what I did there, champ? Yeah. Well, it's been a while since we taught trig functions. So what about if f of theta is 9 sine theta plus 10 cos theta? What's the derivative of sine theta? Okay, so what's the derivative of 9 sine theta? 9 cosine theta. All right, what about the 10 cos theta? What's the derivative of cosine? So the derivative of 10 cosine theta is negative 10 sine theta. Man, you guys are great. Okay, so that's pretty easy, right? Now, warning, this does not work with multiplication and division. Okay, there's other rules for that are a bit more complicated. So it is unfortunately not true that the derivative of a product is the product of the derivatives. It turns out to be more complicated than that. And we'll talk about that on Monday. Which actually I should mention, Monday. Dr. Gates will be teaching for me because I have to be doing interviews all day for a scholarship thing. And so what that means, though, is if for some reason any of you guys are not going to be here in person, he needs to know so that he can set up. I'm not sure if he's going to use Zoom or if he'll do Twitch himself, but I'll have him send you all that info if needed. Okay. Yeah, so it may not be on my Twitch. Well, it won't be on my Twitch channel on Monday because he doesn't have access to it. Although, actually, I think I can delegate it so that he could. I'll have to look into that. Okay, but anyway, you'll have a substitute on Monday, so don't Don't do like you guys did in high school. Did you ever play games when you had a substitute and like trade names or, yeah? You seem like you were a big troublemaker in high school.
I just thought my name was Dick. I'm Dick the whole class.
Where's Balake at? Right? Aaron. Where's Aaron? Yeah. So, if you want to use some silly ass name, I'm gonna. I love that sketch. Okay. Anyway, so let's keep going. 7e to the r. What's the derivative of 7e to the r? 7e to the r. Okay. Because what's the derivative of e to something? Itself, right? And then the 7 just hangs along. Ah, but wait, there's more. Let's look at d. What's the derivative of natural log of x? 1 over x. So what's the derivative of 2 natural log of x? Okay, so 2 over x minus 1 plus, it's a trap. Dang it, I have it in my office. I have a full-size page picture of Admiral Akbar that says it's a trap, and it's laminated, so I can hold it up and be like, it's a trap. What is pi? Right, 3.14, blah, 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 blah. It's a number. What's e? 2.718, blah, 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 blah. It's also a number. What's a number raised to the exponent of a number? It's a number. What's the derivative of a number? Gotcha. Bazinga. Yeah. Actually, did I tell you guys about my Bazinga button? Or my easy button? Huh? At this hour in the morning? Well, I did kind of go to bed early last night. I was just like, screw it. I don't feel like watching NCIS, so I'll go to bed.
So what's the final answer to D?
To D, it'd be 2 over x minus 1. That's it. Okay? And the reason that there's not a a third term there is because pi and e are constants. So the derivative of a constant is goose egg, right? Okay. So this is, I tricked you guys on that one. Okay? If it looks like a constant and it walks like a constant, it's probably a constant. Okay, so just be careful. Okay, so yes, 2 over x minus 1 plus 0. Okay? All right, so the last one here, let's see. The equation of a tangent line at x equals pi halves. Oh, no. What's the problem here, Dr. McKinney? Let me go back to my sheet. Because, all right, so actually let me just go to a clean page here. F of x equals 4 sine x tangent Okay, what 2 pieces of information do we need to come up with the equation of a tangent line? We need a point and we need a slope. Do we have a point? Well, we have half of the point. We know it's x coordinate. How do I get the y coordinate? Yeah, plug it into the original function. Okay, so the point is going to be at pi halves, that was the given x coordinate, comma f of pi halves. What is f of pi halves? Well, it's 4 times sine of pi halves. What's sine of pi halves? 1. And so 4 times that is 4. We all remember our unit circle, correct?
No.
You're about to, right? Okay, so you guys, the special angles on the unit circle, sine and cosine and tangent of all of them, is going to get crammed into our brain over the weekend, because otherwise the beatings will continue until morale improves. Yeah? And I've got the stick over here. I know how to use it. Yes, so you guys unfortunately will have to be good with your unit circle. Yeah. And I have been known to give punishment quizzes over that, so don't make me do that. I'll turn this classroom around right now. I'll do it. All right, anyway. Okay, so there's the point. What about the slope? Well, what do we need to know for the slope? Yeah, we need to know the derivative, which is what, Mr. Amore? Negative? Yeah, okay, careful. And then I need to plug in pi halves to this one to get the slope. And what's cosine of pi halves? 0. Okay, that's actually kind of nice because what does that mean the equation is? In point slope form, it would be that. So just y equals 4, okay, as a function. Okay, so does that kind of make sense? Okay, good. All right, then the last thing I want to talk about just briefly is, I'll have to have Dr. Gates come back to it just briefly at the beginning, which is we can talk about multiple derivatives. So if I take the derivative of a function, and then I just sort of say, oh, well, can I take the derivative of that derivative? Sure, and I could keep doing that as long as I wanted. That's what we call multiple derivatives. And in in Newton's style notation, you just put more primes on it, okay? Except when you get beyond 3 primes, do you want to write like 16 primes? No, that would be annoying. And so what we do instead is we either write the number in parentheses, and the parentheses are important because that tells us it's not meant to be treated as an exponent, but rather as the number of times we did the derivative. I have also seen it, although this is pretty rare, where you write the number as a Roman numeral instead, but that's, like I said, kind of arcane. Okay, Leibniz notation is a little messier. But that's what it looks like. Okay, and the reason that we care about this, and this is what we'll have to come back to, and that's okay, is physics, okay? Because if a function represents the position of an object, what does the derivative represent? Its velocity. What's the derivative of that represent? The acceleration, okay? What's the derivative of the acceleration called? Do you guys happen to know? Huh? It's jerk. Yeah. And then the 4th, 5th, and 6th derivatives, I am not making this up, are called snap, crackle, and pop. Yes. Yeah. The physicists came up with that one, right? But anyway, so acceleration, velocity, position, right? Those things really are code for derivatives, okay? Or derivatives of derivatives. And knowing that will allow us to do some sort of basic physics kind of questions, which we'll have to come back to later. Okay? All right, so I'm sorry I left the things at home. I will give those to you guys on Monday. You guys did pretty well. There was one mistake on it that, you remember the one where I gave you the table of values and I asked, is it reasonable that the limit is whatever? Well, I accidentally had 2 values backwards when I was copying and pasting them. And so some of you were like, no, because this side's decreasing, but it should be increasing. That was correct. And yeah, so anyway, I gave that to everybody because I was just an idiot. You guys were all, the answers were all reasonable, so that's good. All right, well, have a good Monday and be good for Dr. Gates, and I'll see you guys Wednesday.